Hello everybody, TYAN here, configuration there. This is Stef from Samayas and welcome to my channel. Today I'm going to go in deep into the BIOS settings of the TYAN GT86C-B5630. This is a continuation video on my previous in-depth review of this TYAN server. So let's dig in. Now let's press F2 to enter the BIOS. Now we can see all disks identified. And the main screen is pretty basic. We have the server name, we have the BIOS version, we have the build number, access level, we have the processor type, its revision, memory information, and date and time. Now let's have a look at the advanced setting. And so the first option is the trusted computing. And so this line is present since I have a TPM module in the system. So let's go in there. So trusted computing refers to a set of security technologies that use hardware-based security features, like verify the system integrity during boot, provide secure storage for cryptographic keys, enable remote attestation of system state, and support systems like BitLocker on Windows. With the current state of things, TrueNAS and TrueNAS Scale don't really support TPM. So whether or not you have a TPM in your system doesn't really make a difference. So the first option allows us to enable or disable it. For now, I'll leave it enabled. And so currently, as you can see, the TPM supports SHA-1 and SHA-256. And both are enabled. Let's say in the future, when SHA-1 is really considered to be unsecure, we could disable it. Just by clicking Enable or Disable. Our current pending operations on the TPM is none, but should we need to, we could choose to clear it by selecting TPM Clear, and so on next reboot, the TPM information will be cleared. So if we jump to the bottom and we choose Device Select, in there we can see we have a choice to support either TPM 2.0, TPM 1.2 or Auto. For now, I'll leave it on TPM 2.0, which offers the most options. So TPM 2.0 implements a hierarchical structure that organizes cryptographic objects and access control into 4 distinct hierarchies. TPM 1.2 only has a single hierarchy. So the first hierarchy we see here is the platform hierarchy. This is mainly for OEM, and this controls the early boot firmware shipped with the platform. The second hierarchy is a storage hierarchy. These are controlled by system administrators and users for general TPM operations, like clearing. And the third hierarchy is the endorsement hierarchy, which is administered by privacy administrators and manages privacy-sensitive operations. So out of the block, those 3 hierarchies are active. So if I disable the platform hierarchy, then the firmware will not be able to do any actions on the PCR bank, like clearing or adding or updating trusted keys. If I disable the storage hierarchy, an administrator cannot manage, access or update cryptographic keys in a TPM. And if I disable the endorsement hierarchy, then privacy-sensitive operations are not allowed on the TPM anymore. TPM 2.0 UEFI spec version, so even though if I select the TPM, I can still have the TPM 2.0 configured to use TPM 1.2. The physical presence interface defines how a user or operator can provide physical presence to authorize sensitive TPM operations, such as enabling, disabling, or clearing the TPM. Version 1.3 is the upgrade of version 1.2, which has better separation of hardware versus command method and asserting presence. PH randomization stands for Platform Hierarchy Randomization. This feature is designed to enhance the isolation and security of platform hierarchy. But then again, on any computer, on computers, random doesn't really exist. Next we have ACPI settings. Let's go in. So ACPI refers to Advanced Configuration and Power Interface. It's an industry standard specification that enables operating systems to manage, configure, and power management functions on a computer system. These settings determine how hardware components are powered and how much your CPU is using or not, when it's going to sleep, when it wakes up, etc. So when the Enable ACPI auto configuration is on, then we have maximum hardware compatibility and the OS can control everything in detail. So this option should really be on. However, When this option is disabled, then an OS can't really control anything, and your system will run all the time the same, at full power, at full speed, etc. As you can see, if I enable, the hybridization option disappears. If I disable, I have the explicit possibility to enable hybridization or not. Again, for me that's an option which doesn't really make sense on a server, since the server will be running on 24/7. The enable hybridization can be activated or deactivated. So let's put auto configuration again to enabled, and now the system can do whatever it needs. Next, we have the hardware health configuration. Let's go in. Here, technically we can decide what the speed of the fans is. Automatically, and the system will do it. If you put on manual, that would be a way to reduce, or if you put on full speed, the fans will be blowing 100%. In general, automatic is the best option. The BMC alert beep can be enabled or disabled. Depending on where your system is located, having that beep on or off does make sense. In general, on most servers running in a data center, that doesn't make sense at all. There's remote reporting and it's better. And whether or not you have 1 or 48 servers, each beeping because of the issue, you won't even notice. At best, you might notice that rack is something is beeping, but before you located it, it's not the best option, but it's available. Now, if this is only your only server at home, well, having a beep at it is perfect. Next, we have PM bus support, which you can enable or disable. PM bus stands for Power Management Bus. It's a protocol and physical interface for monitoring, controlling and configuring power converters and other power-related devices. So in essence, if you enable this, through further monitoring, you can see voltage, current, temperatures and status of your BMC and PDU, and so it's best to have it enabled. Next, we have the number of PSUs. In my scenario, I only have one PSU in the server, so I only have one. And finally, I have a sensor data register monitoring, and if I go in detail, it will start reading some of the sensors in my system, which I can also do through IPMI. And here I can see temperatures for my CPU, for the speed of my fans, etc. The voltage used currently, the PDU status. Next, we have the onboard device configuration. That's an easy one. I can enable or disable the onboard VGA. If I disable the onboard VGA, the only way to still access the system and the BIOS settings would be through the IPMI interface. In general, the only reason to disable an onboard VGA would be if you insert a second VGA card. Next, we have the AST2500 Super I/O configuration. The AST2500 is this BMC or motherboard, and I/O configuration refers to input-output. And so here I can configure the serial ports. So the motherboard has 2 serial ports, even though only one physical serial port is present in the back. So let's have a look at what we can configure at the serial port configuration. In general, we can decide to enable or disable it, depending on whether or not we need it, and then we can specify on which IRQs this is running. We can leave it on auto, or we can specify the IRQ we specifically need. For those who remember IRQs from the old days, in the 90s, when you put it in one or more COM ports and or one or more modems, each of those modems needed to have a unique IRQ. If not, the modem or the COM port wasn't working. It was always quite a hassle just to find the free IRQ code. So this setting throws us back roughly 30 years. In general, if you even use a serial COM port, well, it might be just to output to console, but some computers and some devices still require COM. So it's available and you can configure it. Next, we have the S5 RTC wake-up settings, and in here we can choose to disable it, to have a fixed time that the system needs to wake up, like every hour at 7 in the morning, or a dynamic time where it increases every time by 5 minutes. Personally, a device like this doesn't need any wake-up, it's running 24/7. Next, we have serial port console redirection. This allows us, in case we don't have any monitor, to still through serial port by using a serial port cable to USB, for instance, to see everything which is happening on the server, pure in text-based. Or, more often, by using an IPMI redirect to see on a remote machine what is happening on the console. Since this machine has 2 COM ports, COM1 a physical and COM2 a virtual, we can choose which one the console is redirected to, or both if you want to. I can enable or disable it, and I have console redirect settings where I can specify what the terminal type is, which can be VT100, VT100+, VT UTF-8, or the older ANSI. I can then further specify the bitrate per second, the data type, and a parity and the stop bits. I can specify whether or not there's a flow control or not, whether or not I still should enable VT UTF-8. The record mode allows to be sent text only or not, and the resolution can be forced to be 100 by 31. And finally, I can enable the type of keypad. For COM2, I have exactly the same number of settings. And then finally, we have a number of extra legacy control redirecting settings. These are specifically useful if you are running systems which are non-UEFI compatible. If you go in here, we can choose to redirect to COM1 or COM2. We can force the resolution 80 by 24 or 25, and we can force the always redirect or just after the bootloader. And next, we have the serial for out-of-band management and the Windows Emergency Management Service, which allows to remote control and troubleshoot a system even when the operating system is not yet running or has crashed. Here again, we can allow to enable or disable the console redirections in either of those cases. And if we enable it, again, we can specify which COM port to use, what terminal type to use, the bits, the flow rate. Next, we have option ROM dispatch policy. This is a policy that dictates how and when the firmware will execute option ROMs, firmware modules present on add-on cards or other onboard devices during the boot sequence. And as you can see here, I currently have a PERC controller in there, and I can decide whether or not my PERC mass storage is enabled or disabled. Should I not have had a PERC controller, then this line would also be empty. I cannot change anything else since my system is purely in UEFI, and UEFI will decide what happens in what order. Next, we have the PCI subsystem settings, and in here I can decide how PCI should behave with above 4 GB decoding. So these are advanced options controlling how the motherboard manages and allocates PCI and PCI Express devices. One of the most notable that you find in most motherboards is the above 4G decoding. The above 4G decoding enables the use of memory addresses higher than 4 GB for PCIe and PCI devices. This is much more important for systems with large amounts of memory and a lot of PCIe devices, such as servers with multiple GPUs, storage controllers, network controllers, etc. Traditionally, 30-bit addresses are limited to 4 GB. In essence, by enabling this, we enabled 64 capable devices to assign memory addresses in regions above 4 GB. The SR/IO virtualization support enables PCI Express devices such as network adapters and storage controllers to present itself as multiple independent virtual devices to the system, each of which can be assigned then directly through virtual machine. So in essence, one physical PCI devices can be presented and split into multiple virtual PCIe devices. If you're running this server as a virtualization server, this makes sense. If it's a storage server, it makes a lot less sense. And so the SR/IOV support for this server should rather be disabled. So next we have the USB configuration. Under that, first we have legacy support. Legacy support settings allows USB keyboard and mouse and flash drives to work even before any OS is loaded. Next we have the XHCI handoff. When enabled, the BIOS hands over the control of the USB 3 to the operating system using its own USB drivers. If it's disabled, the BIOS keeps handling USB 3. So if you're just using keyboard and mouse, it doesn't really matter. However, if you're using it as a boot drive or some other kind of devices, that makes a difference. The USB mass storage driver support allows you to enable or to disable the ports to be used as masked storages, meaning as boot drives. If you completely want to secure and you passport protect the BIOS and want to be sure that nobody can boot through an external drive, by disabling this, an external USB drive won't be recognized as drive and won't be bootable. I've left it enabled to be able to install my OS, Trunas, etc. And next we have port 60/64 emulation, which allows the motherboard to emulate traditional I/O ports, for instance like using classic PS2 keyboard for USB keyboard and mouse. Some legacy OSs still require it. Most modern don't really need it. For now I've left it, but you can probably disable that. And then finally, the USB transfer timeout is a setting to control how long the system waits during data transfer or data initialization of USB drives, particularly during pre-boot operations. Typical values are between 1, 5, 10 or 20. 20 is a default and the max. The purpose is to prevent indefinitely stalling if a USB device drive is too slow or unresponsive. The USB reset has values from 10 to 40, where 20 is a default. This allows even slow starting USB drive to properly initialize. And then finally we have the device power up delay, which can be in automatic or manual, where you can decide the number of seconds needed before the device is powered on. Next we have the network stack configuration. If we choose to, we can completely disable it. If you don't need any PXE or network boot, it's probably better to disable it. By disabling it, you will have no PXE, you have no network boot. In your boot options, you won't see any network interface. If you enable it, you can choose whether or not to enable PXE for IPv4 or PXE for IPv6. And PXE stands for Pre-Boot Execution Environment. It's a standardized client-server protocol that allows computers to boot up and load any operating system from a remote network drive. That implies that somewhere on the network you have a PXE server, a DHCP server, and a TFTP server. And lastly, we have the IPv4 HTTP support and an IPv6 HTTP support. Of course, this implies that you have an HTTP server on the other side, which can service the image you want to load, rather than using the standard TFTP. We can also configure the PXE boot wait timeout, which is the number of seconds it waits before trying to reach the server. And finally, the media detection count is the number of times it will try to reach your server, be it in TFTP or HTTP, and try to retrieve the image it needs to start. After those number of tries, it'll fail and try the next boot option. Next, we have a CSM configuration. CSM stands for the compatibility support modules within the UEFI BIOS firmware, and for each of those individual components, network, storage, video, and other PCIe devices, we can choose whether or not it needs to be handled as a UEFI or as a legacy. For those of you who have been paying attention, we already saw those options when going back to the other ROM display. However, those four were read-only. By changing the CSM configuration, now we can clearly see that the other ROM options has changed as well. Whether or not you want to put everything in UEFI or rather legacy will depend on the OS you want to run on this system. Systems like Windows support UEFI, other systems, Linux-based, sometimes don't support it yet, and that'll define which choice you need to make. If I completely disable it, it'll boot in fully UEFI mode. By disabling it, if we go back to the other ROM policy, it has changed as well, and it's completely switched into UEFI. So depending on whether or not you want fine-grained control, you'll enable it or you'll disable it. Disabled means default mode is UEFI for all. Enabled, you can switch back if needed. Next, we have the NVDIMM and ADR configuration. NVDIMM stands for Non-Volatile Dual In-Memory Module. ADR stands for Asynchronous DRAM Refresh. This mechanism, if enabled, ensures data persistency on NVDIMMs during sudden power loss. ADR is a hardware feature where upon power loss, the motherboard signals the memory controller to rapidly trigger a save process using residual power from capacitors and batteries or supercapacitors. Any unwritten data in DRAM which reaches the memory controller is quickly flushed and committed to persistent data storage. The ADR mechanism is entirely hardware controlled. No software or operating system is involved. This feature is supported on this system and motherboard, but for it to enable to work, you need to have special DIMM. And normal DIMMs, RDIMMs, LDIMMs, etc. don't support it. So even though out of the box it's enabled, since I don't have any of those DIMMs, I should disable this. Next, we have the RAM disk configuration. As the name implies, we convert RAM memory to disk. Back in the 90s, when disks were small and very slow, it was very normal to transform part of the memory where we could store certain data on for faster access. Back to today, disks are faster, we have NVMe drives, we have SSD drives, etc. On the other hand, memories become cheaper as well, and a lot of systems supports a lot of memory. It is still supported. Whether or not that is a good idea depends on what you want to do with the system. Do keep in mind that all the data on that RAM disk, the moment the system reboots or crashes, it is gone. So in essence, if you want to use that, that's something for caching or some other volatile memory. But on the other hand, if it's only for caching, do you really need a disk? Can you just not use some other kind of programmatic storage? But it's up to you. It's possible. So in essence, we have two modes. We have the boot service data and we have the reserved. In the boot service data, we can create a RAM disk, which can only be accessible during the boot phase, and the moment the boot phase is over and the real OS is ready, that part of the memory is liberated again. If you use the reserve part, however, that memory will be allocated for a RAM disk the whole time until you reboot and/or change your configuration. A real-world example for the boot services data would be a Linux or Windows installation environment that uses an initial RAM disk. During the UEFI boot, the firmware may extract a RAM disk image from the boot devices, such as an USB, an ISO, or a network server, and load it into the boot services data. This RAM disk then contains a minimal environment, kernel, tools, install programs for the OS to be installed. Once the OS is installed, the RAM drive is discarded. In general, when this feature is supported, Windows or Linux will use that out of the box, and you don't even need to manually create a RAM disk yourself. The OS will handle that themselves. Now, if you want, we have a RAW, where we can create a raw RAM disk or create from file. Create raw demands a size. Let's create it. And here you can see I have a first RAM drive. Create from file will ask for a specific file. And we'll create RAM drive from a specific file. I just selected the first file, but in general that should be an ISO or something. But it really depends what you want to do with it. So next we have the iSCSI configuration. So iSCSI stands for Internet Small Computer System Interface, and it's a network storage protocol that allows computers, clients and servers to access and use remote storage devices over an IP network, as if those devices were directly attached. Now in essence we have in iSCSI two roles. We have the target and we have the initiator. And so technically iSCSI configuration should be called iSCSI initiator configuration, because this system here in the BIOS only supports the initiator role as a client. Of course, if I install the right software on this server, I can make it also an iSCSI target. But the goal here, by configuring the BIOS, is to have a remote target used somewhere as a disk. That might be a boot disk or whatever. And so the first thing you need to do is to specify a name of your initiator. So as my initiator name, I choose iqn.2025-09-eu.samayas, and my test server is called testnas, and that's a valid name. Valid names must start with IQN. Then in general you have a syntax of 4 characters for the year, -2 characters for the month, then the naming authority, and finally a unique name. Next we have add attempt, delete attempt, and change the order. The add attempt allows me to add a specific initiator. Since my server has 2 SFP+, I have 2 MAC addresses. I'll choose the first device, and here I have my first attempt. I have an iSCSI mode. In iSCSI mode, I can leave it disabled, I can enable it, or I can enable it for MPIO. MPIO stands for multipath I/O, which allows the same iSCSI target to be approached through redundant network paths for improved reliability, load balancing, etc. But that again depends on your network configuration, your requirements, and your resilience. Next I can choose whether or not I use IPv4 or IPv6, or I don't care. I can enter the number of times it retries. I can specify the timeout. The ISID stands for the Initiator Session ID, and that's a unique identifier generated by the iSCSI initiator client in order to uniquely identify itself in the target or the server. Now this value is auto-generated, but for whatever reason you can change it if need be. Next we have the possibility to enable DHCP or not on the device and automatically receive an IP address or hardcode the IP address. Again, that depends on your system, the number of network cards, and whether or not on that particular connection between your client, iSCSI initiator, and your server target, there's a DHCP server or not. And finally, if DHCP is enabled, you might also get the target name if your DHCP server supports it and you want to configure that. And then we have the authentication type. Depending on how secure or not, it's always a good idea to secure that drive, because if somebody else finds out the target, he might just retrieve everything on that drive. And then once you configure CHAP, you can configure one way where the client authenticates, or mutual where the client needs to authenticate with the server, but the server also needs to authenticate with the client. That way we avoid impersonification of the server. Now once we added an initiator, we can also delete an existing one and remove it. And finally, if we have multiple initiators, we might change the order on who takes precedence. Next, we have a configuration option for the Dell perk which I've inserted in the PCIe. Technically, if this device wouldn't be there, I wouldn't have this option. But here, based on what is attached to this perk, I could configure whatever I need. Currently nothing's attached, so it's just clear. Next we have the Intel Ethernet OCP server adapter, which is my dual SFP Plus card. In here I have NICs configuration. I can have it wake on LAN. Technically this server will never be woken on LAN, so I can disable that. I can configure VLAN, but currently I don't need it. I can have it blink, and I can't really change anything else. And if you look clearly, there's a second one here as well, since even though it's the same card, in the configuration it shows up as two individual lines with separate MACs, etc. And then even though I have a VLAN ID specifically on the Intel card's NIC configuration, I still have a separate VLAN configuration for that card, where I can specify more or less the same. Let's check if I change it here, if the other one would change as well. And if I go back to the first, the VLAN ID doesn't change. So which of both configuration is taken into account, I have no idea, but I don't plan to make any VLAN configuration specifically here, but rather in my OS, should I need it. And of course, for the second card, I have exactly the same VLAN configuration. And then finally, I have two MAC lines, IPv4 and IPv6 for my first card, and two IPv4, IPv6 for my second. If I go to IPv4, I can enable configuration, and I can use a DHCP, or I can hardcode IP address, MAC address, gateway, and DNS server. Same thing for my second card. And same thing for the IPv6 configuration. Why this wasn't regrouped, I don't know. Next, we'll have a look at the platform configuration. This refers to a collection of system firmware settings that controls how the hardware platform operates, initializes, and interacts with the installed operating systems and devices. In there, the first subconfiguration is the PCH configuration. The PCH configuration is a shortcut for Platform Controller Hub, which is Intel's new single-chip chipset that manages many of the central I/O and peripheral functions on a modern motherboard. The PCH replaces the old Northbridge and Southbridge chipsets, combining I/O, connectivity, and legacy support into one new single chip. It handles the communication between the CPU, the devices such as SATA, NVMe, USB, and PCI Express slots. Now if we go into detail, the way the system is composed, we have a SATA configuration and we have an SSATA configuration. Now if you go back to my hardware video of this system, you can clearly see that we have 3 rows of 4 hard drives, plus an extra boot drive in the back behind the PDU. Now each of those rows has a backplane wherein the hard disk is directly connected to, and so we have technically 3 backplanes, and those backplanes connect via a specific cable to the motherboard. However, probably because it's less expensive hardware, for instance, if I compare with my Dell R730, I have 1 backplane and all my 12 disks are connected to either a local software controller or a RAID controller. In this scenario, the first 8 disks are connected to my PCH SATA configuration, and the next 4 plus the boot are connected to the SSATA configuration, which means both are clearly devised. Now let's have a look at our specific configuration. Of course, we can enable the SATA controller or not. In some systems, we might have diskless system and run everything through iSCSI. This is clearly a server which is made as a NAS, and so disabling the SATA controller doesn't make any sense. The next, configure SATA, allows us to configure the SATA controller either as an AHCA controller or as a RAID controller. And so the controller/motherboard supports software RAID. Now first of all, my goal of using this system is to run it through NAS and play around with ZFS. And for ZFS, it specifically asks not to have RAID underneath and to provide each of the disks individually. Now, even though if you would use this server for some other OS which is not using ZFS, the RAID still has issues. Technically, I have 2 RAID controllers and I can't create one big RAID partition. My first RAID partition can use 4 disks and my second RAID partition can use 8, but they're never really regrouped. Now, if I want to enable a RAID controller, I first need to select RAID here. I need to save everything, and then in reboot, I will have access to RAID. So we'll look at that later. The support aggressive link power management is a power saving feature for SATA drives that puts communication link between the motherboard HDI controller and SATA devices in low power state during periods of inactivity. The benefits, of course, are energy savings. However, it might also create potential latency and compatibility issues with certain systems. When running systems like TrueNAS and ZFS, it is not really advised. If you're running other systems, it might be less risky. The biggest risk, of course, is the stability. Performance is something you choose. Personally, I've left it disabled. Next, if we switch back from AHCI to RAID, we have 3 more options. The SATA RSTE boot information, when enabled, allows the system to boot directly from a RAID partition. If however you have a boot drive and you still want RAID, then you don't really need that. The alternative device ID on RAID or storage controller BIOS configuration is how the controller identifies itself to the operating systems and drive. The load EFI driver for RAID is something which is needed if you want to boot directly from a RAID device. If not, you don't really need it. The next, for each of those ports, you have an option to enable or disable. When you're running a NAS system, having a hot pluggable enabled might be a good idea. That means you can swap a drive for another if a drive is crashing, without having to reboot the system. And the eSATA setting is mainly something for external SATA ports and not internal ones. So even the option is available, that should stay disabled. And finally, for each of the drives, we can choose to specify whether it's a hard disk drive or a solid state, in case the system didn't detect it. And finally, if I look at my second controller, the first 4 disks are hard drives, and now detected out of the box. The 5th has nothing, and the 6th was detected as a solid state drive. Next, we have our USB configuration. The XHCI idle level 1 is sometimes called USB Link Power Management Level 1, which refers to the USB power saving features, where a controller puts USB links into the deep lower power state. When enabled, USB devices like keyboards, mouse, flash drives, etc. can go into a deep lower power state. Now, if you're using your USB port of this server as a boot drive, then this idle level 1 should be disabled. And then finally, we have the ADR configuration. In this context, the ADR stands for asynchronous DRAM refresh, which is a hardware feature to protect and preserve data in server memory, especially the NVDIMM. We've already seen that in the options before. So in my system, since I don't have any NVDIMM, this should be disabled and all the options are gone. The ADR GPIO configuration refers to the selection of the general purpose input-output pin that the system uses to signal or trigger the asynchronous DRAM refresh. And in this system, if we have NVDRAM, we can choose either B or C, and GPIO pin B is a default. The host partition reset ADR enabled controls whether the asynchronous DRAM refresh mechanism will be triggered automatically when a host partition resets, a specific type of hardware reset, or a multi-partition or highly available system reset. In enterprise servers, resources like CPU, memory, and peripherals can sometimes be divided into independent host partitions for high availability, logical separation, or virtualization. When this option is enabled, if a host partition reset occurs, the platform will fire an ADR signal, ensuring all dirty memory is forcibly flushed to the NVDIMM persistent storage, maximizing the data protection for applications relying on persistent memory recovery. The enable-disable ADR timing setting controls whether a timer is used during asynchronous DRAM refresh process, which is triggered during events like power loss, partition reset with NVDIMM. And when it's put and held off, we have no extra options. When it's enabled, we can specify 100 nanoseconds, 50 nanoseconds, 25 nanoseconds. And we can add a multiplier from 1 to 96. But since I don't have any, I'll just disable it. The grading power-up is also often called the staggering spin-up or power-up in sequence, intended for systems with multiple hard drives or SSDs attached to SATA. And so when disabling this option, all drives spin up and power on. When choosing SSU or staggered spin-up, drives are spin-upped one after the other, with a brief delay between each. This reduces the inrush current and load on the power supply. The PUIS, or power-up in standby, leaves drives in a standby mode after power on. The default option is a staggered spin-up. And if we have selected either an SSU or PUIS, we can have a sub-mode, all, or DC for direct current, or AC for alternating current. And the distinction between AC and DC is that AC is considered a cold boot, while DC is considered a soft reboot or a reset. The default is also for all modes, and the interval delays between the drives is 5 seconds. The next option is completely unrelated, and it's restore the AC power loss. The three possibilities are S5, last state, or random power on. S5 is considered a soft off, which means that even though the system has power again, it won't boot up. The last state, depending on whether the server was on or off, will turn it on or off again. And random power on will power it on or not with whatever random value. And if you have a power outage and you have a rack with 48 servers, you don't want them to start up all at once. So you can include some random power delays. Server 1 is booting after 1, server 2 is booting after 10, server 3 is booting after 3 minutes, etc. The next line, DCI enabled or HDCIEN, is a direct interface between Intel hardware and debugging and tracing interface. DCI allows a direct connection between system Intel debug tools and providing low-level chip debugging. For most systems in production, DCI enabled should be disabled, since there's no need. And then related to the first, the DCI Auto Detect enabled detects the configuration of Intel Direct DCI settings for hardware debug and tracing. And again, on a production server, this should be disabled. Next we have the miscellaneous configuration, and here we can choose whether or not we're using the onboard video device or an offboard version. And then finally, we have server ME configuration, and that just shows firmware versions. Next, we have socket configuration. The first line is the processor configuration. And in here, first I see the details of my processor, which is a 5654, which is an Intel 4114. Hyperthreading is enabled, and enabling allows each physical processor core to appear and function as two logical cores, letting the processor handle more simultaneously threads. Disabling hyperthreading means that each core can only handle one thread at a time. Since the NAS will next to copying also handle a number of other processes, it seems a good idea to have this enabled. The max CPU ID value limit controls whether the processor restricts the range of CPU ID instruction values it reports to the operating system or not. The default is disabled, and that means that the CPU reports the actual maximum CPU function values, allowing modern operating systems to have an ID of all features of a CPU. When it's enabled, process limits the maximum CPU input values to 3, even if the CPU can answer higher CPU instructions. This makes the CPU appear as if it only supports the most basic functions. To enable Intel TXT or Trusted Execution Technology is a set of security features in compatible Intel processors and chipsets designed to create hardware-based tamper-resistant environments. In general, this is a function that is enabled on enterprise server, data centers, and highly secure environments. For home users, that doesn't really make any sense. However, since we're going to run a NAS on this, enabling it seems like a good idea. The hardware prefetcher is a CPU feature that automatically fetches instructions or data from system memory into the cache before the processor actually needs it, based on detected access patterns. By default, it is enabled and recommended. This increases the performance in most general purpose and scientific workloads, and apparently it's only rarely needed to have it disabled. In cases where there's very specific latency sensitive or low-level applications where prefetching might occur and pollute cache and reduce effectiveness, there it should be disabled. In line with the previous hardware prefetcher, the level 2 RFO or read of ownership is also a form of prefetcher. When it is enabled, the processor prefetches data from memory into level 2 cache, again in anticipation of what the CPU core will modify, write to, or soon. This can be especially helpful with workloads with predictable write patterns, as it might reduce latency by getting the data cache line ready for immediate write. When it's disabled, the processor only fetches cache lines on the actual write operation or read misses, which can introduce additional latency on write-heavy or pattern workloads. Disabling it might be very beneficial in specific use cases or when experimenting with very random memory write patterns. So in general, having it enabled also seems a good thing. Now here it's quite tricky, because the L2 LFO prefetch disabled is disabled, meaning it's enabled. And if I'm enabling it, I'm disabling it. The adjacent cache prefetch is a CPU cache feature that automatically fetches the cache next line to the one being processed by the program, bringing both lines into the cache at once, even if only the first one is executed. Again, this is enabled by default, and disabling it only makes sense in workloads with very highly random access patterns. The extended APIC refers to the modern enhancements of Intel Advanced Programmable Interrupt Controller architecture used to manage hardware interrupts efficiently, especially in multi-core or multiprocessor systems. Now the system is multi-core, but not multiprocessor. And the extended APIC refers to the newer generation of the APIC architectures. Enabling the extended APIC allows operating systems to take advantage of improved interrupt routing necessary for modern multi-core CPU and server environments. So again, this one should be enabled. And disabling the extended APIC is almost never recommended. Only when you have compatibility issues should be disabling it. And finally, the AES-NI stands for Advanced Encrypted Standard New Instruction Set. It's a set of special hardware instructions built into modern Intel and AMD processors that dramatically accelerate the performance of AES encryption and decryption operations. And this is very important if you want to encrypt or decrypt your NAS drives. So again, this should be enabled. Next, we have the common ref code configuration. This refers to low-level platform and chipset initialization settings provided by Intel's reference code, often called ref code, for servers and high-end desktop. The first setting is the MMCFG base, which is a setting that specifies the starting physical address in system memory space, where the configuration space for PCIe Express devices is mapped. The purpose of the MM configuration base tells the system where to reserve memory regions for PCIe configuration registers, allowing the operating system and firmware to manage and communicate with PCIe devices using mapped memory I/O rather than legacy I/O ports. Typical values are 1 GB, 1.5 GB, 2 GB and 3 GB. So next to the MM configuration base, we have the MM configuration size, which refers to the amount of system memory which is reserved specifically for PCIe Express devices. Depending on the number of PCIe devices you have in your system on one side and the memory you have available on the other side, you can play around with this and provide more or less. The minimum is 64 megabits, the maximum is 2 gigabit. This size is what the system will reserve specifically for this management. Next, we have the MMIO high base, which is a UEFI setting that defines the starting address of high regions reserved for memory mapping I/O in a server and a workstation. The goal of the MMIO high base is to set the lowest address at which these high MMIO regions begin, which should be typically higher than the available memory. So currently this is put at 3 terabytes. Now if in my system I would be setting 3 terabytes or 4 terabytes, I should go from 3 to 4 to 16 and I can go to 65 terabytes. Since I don't have 3 terabytes in the system, the high limit of 3 terabytes here is fine. And the MMIO high granularity size determines the allocated unit of granularity for reserving high memory mapping address, which is used by PCIe devices and other peripherals that requires memory mapping regions above the physical RAM. The larger the granularity, the more the BIOS can ensure sufficient continued address space for high MMIO regions, avoiding problems where big PCIe devices such as modern GPUs or NVMe SSDs fails to get enough MMIO address spaces. So larger values like 265 GB or 1024 GB is important on servers with many PCIe devices and huge memory. And then finally, NUMA stands for Non-Uniform Memory Access, which is a system architecture used in multiprocessor or multi-core server platforms to optimize memory access as system scales and performance as system scales up. In a NUMA system, each processor or a group of processors is called a node and has its own logical memory. The operating system must be NUMA aware. In general, enabling NUMA does not provide any practical benefits since there's only one processor, and enabling it only makes sense on dual CPU or quad CPU systems. Now, even if it is enabled, it won't negatively impact single-core systems. Next, we have the UPI configuration. UPI stands for Ultrapath Interconnect Configuration. This is a setting that manages low-level setup and performance parameters of point-to-point links used by Intel processors to communicate directly with each other in multi-socket platforms. So first we have the status, and as we can see, we have one CPU, we have an ID of 1, the current UPI link is slow or 1 second configuration, the current UPI link frequency is unknown or 1 second, and we have a number of memory addresses. Our link speed mode controls the data transfer frequency of the Intel UltraPath interconnect link between processor and multi-socket server systems. On the system currently it's set as fast. Putting it to slow might slightly improve the power efficiency and reduce the heat, should your system overheat. Normally, this should only be tuned for high-frequency trading, scientific or latency-sensitive workloads. So the UPI link frequency select allows us to determine the operating frequency of Intel Ultra's path interconnect. And currently we have the choice between Auto 9.6 GB, 10.4 GB or Use per link setting. Auto is a default and recommended value. Putting it on maximum value is only advised on systems with heavy workload. The UIP link L0P enabled is a setting that allows Intel UIP links between CPU and LOP power state, which is partly low power state to the link. Again, this value is set to auto. The LOP enable allows systems to drop idle UIP links and to preserve power. In the same line, the link L1 enable enables a full link down state, maximizing power savings but increases wait up time and latency. Since both values are in auto, in essence the system manages whether or not it needs to enable or disable it whenever it needs it. And then finally, the UIP SNC refers to sub-NUMA clustering, which is again a feature of the Xeon platform in combination with UltraPath interconnections. Since at first we have a single core and so NUMA doesn't make any sense, sub-NUMA won't make any sense either. On a multi-core system, enabling it reduces every memory access between NUMA-aware processors and the system. This can especially be very beneficial for high-performance clusters, analytics, or in-memory workloads. Next, we have the memory configuration. The first line, enforce-POR, stands for Enforce Plan of Record, and this determines whether the system will strictly follow the Intel-defined Plan of Record limits for DDR4, frequency and voltage programming. When it's enabled, it enforces those guidelines and forces the memory controller to operate within the official validated memory frequencies. When it's disabled, it allows out-of-spec configuration, enabling the use of unsupported higher memory frequencies and voltages, but could also affect the stability. In auto, in essence, it follows the rules, except specified otherwise. PPR type refers to post-package repair, which is an error correction mechanism supported by DDR and memory controller. In hard PPR, the remapping of the faulty DRAM row to the spare row is performed at the factory or as part of the write protect irreversible command. Once a row is replaced by the spare, the changement is permanent. Soft PPR is called dynamic row replacement. In soft PPR, the remapping is handled dynamically and often temporary by the memory controller. When a fault is detected in a row during a runtime, for example, the memory controller just instructs the DIMM to remap the faulty row to another row in a spare. This remapping can again afterwards be cleared after a power recycle. The memory frequency allows us to define the frequency of the memory DIMMs in the system. Currently, it's set to auto. My system contains DIMMs at 2133 and currently the system is configured to work at auto. Depending on a different combination of DDR SIMs in combination with the CPU, your system might decide to work at lower memory frequency. The MRC promote warnings relates to how memory initialization issues are reported during system boot time. The MRC is the component of the BIOS that is responsible for training, initializing, validating the memory at power on. Currently the setting is disabled, and so MRC warnings will not be promoted, minor initialization issues are quietly handled, and the OS or admin may not be notified. When this option is enabled, the system notifies or logs MRC warnings, allowing the administrator or the system to realize there might be an issue. The advanced memtest options is a bit mask which is currently at 81 and it means that multiple tests or modes are enabled simultaneously. The memtest on fast boot is set to auto but can be enabled or disabled. Of course, in general, fast boot implies that less tests will be done. Auto often refers that the memory tests on fast boot will be skipped. ACC checking refers to the error correcting code checking, which is a feature found in a lot of the enterprise server RAM. ACC checking does single bit error correction and it does multi-bit error detection. The erase ARM is specifically for NVDIMMs and it ensures that the persistent memory content of NVDIMMs can be securely erased or prepared, which is armed for erasure. In the same line, the restore NVDIMMs allows it to restore a configuration. Since I don't have any NVDIMMs, I might as well disable those two settings. In the same line, interleaving allows regrouping multiple NVDIMMs into one. This technique is similar to memory interleaving with standard DRAMs, and it brings performance and capacity benefits to persistent memory. And then finally, memory RAS stands for reliability, availability, and serviceability configuration. And currently the mirror mode is disabled, but here we can enable it. Mirror is the same thing as on disk, and so instead of writing something to one memory DIMM, it'll be written to two at the same time, which also means that you halve the available memory on your system, but you have redundancy in return. Using memory rank sparing is a little bit the same. You halve your memory with that difference that instead of using two memory DIMMs at the same time, one is active and the second is ready in case of issues. The correctable error threshold is the number of errors that can occur within a specific time span. If the number of errors is exceeded 49, a warning will be triggered. And depending on whether or not we have sparing or mirror mode, some action might be taken. So leaky bucket low and leaky bucket high is a mechanism for memory error monitoring. It's a mathematical model used to track the rate of accumulation of recurring events, memory errors, and we specify the low level and the high level. The ECC SMI threshold is a configurable limit in server system that determines how many correctable ECC memory errors can occur in a specific time period before the system triggers a system alert. By default, SDDC or single device data correction is enabled. ADDC sparing stands for adaptive double device data correction and is an advanced memory feature in modern server platforms and some high-end memory module systems. ADDC tracks correctable memory errors at a very granular level, bank or rank level. When a memory region, such as a bank or a rank in a DIMM, starts to exhibit too many errors, ADDC dynamically spares out that failing region and remaps it into what's called a virtual lockstep mode. And then finally, Patrol Scrub is a hardware memory feature where the system periodically scans all locations in the system memory in background, reaching each address and checking for errors using ECC. This is also disabled by default. So next we have IIO configuration, and this refers to the integrated input and output subsystem. IIO is the hardware block in the CPU or chipset that manages data traffic between the CPU, PCI Express, and other I/O devices. It coordinates high-speed connections and domain coherence for PCIe devices, accelerators, GPUs, network cards, and storage controllers. First, we have the socket 0 configuration. So socket 0 references the first CPU, and since this system only has one CPU, well, the IOU 0, 1 and 2 refers to the integrated PCIe bridges that manages the integrated I/O between the subsystem and Intel CPU. And by playing around with this here, we could configure it for bifurcation, in essence splitting a card into 4 subchannels. The first two out of the box are configured in x16, the last is configured for bifurcation in x4, x4, x4. And we have quite a few options. We can put it in auto, we can put it in x16, in 2x8, in 8 and 4 and 4, in 4 and 4 and 8, or in 4 and 4 and 4. According to the documentation, BR1 is the only physical PCIe x/16 slot. BR2 is a networking card, and BR3 are additional onboard PCIe devices. Now if you want to, you can always configure it in automatic, and if you don't have any specific needs, that might just work. And as you can see, I have one configuration specifically for my first BR1, I have one for my second BR2, and I have 4 because I have split my BR3 in 4x4x4. If I change my BR3 from 4x4x4 by 16, I would have supposed that those 4 lines would become 1, but apparently they still seem 4. But apparently they still stay as 4 lines. Let's just leave this as 4x4x4. Now if we go into one of those configurations, for each of those PCIe slots we have a number of configuration options. So the first option of PCIe port allows us to let it stay in auto, to explicitly enable it, or to explicitly disable it if you want to block the port. Next, for this PCIe lane, we could enable hot plug capable or not. When enabled, that means we could have hot insertion or removal of PCI Express cards, even when the system is on. Out of the box, that's disabled. Even though this option is available on this server's motherboard, I'm not sure that this server is designed to have hot pluggable PCIe devices. And in line with the previous option, the supplies hot plug refers to the capability of a system to detect and handle unexpected removal or insert of PCIe devices. This is also disabled by default. The PCIe port link determines whether the PCIe link associated with that port is actually trained/connected in the electrical level during boot, but it keeps a port configuration visible to the system even if the link is not established. Say you have a RAID card or an NVMe card in that slot. If that is disabled, the NVMe card will not be found. If it's enabled, during the boot process, that NVMe card can be used. Disabling a PCIe slot might also be a good thing for debugging purposes if you have an issue with any of your PCIe cards. And then next, depending on your PCIe card you put in there, and then the link speed allows you to configure specifically by card what the gen type of your PCIe device is. You either leave it in auto or put it on gen 1, 2 or 3. The PCIe port de-emphasis is a single integrity technique used to compensate for signal loss, especially at high frequencies, that occurs in long or low quality PCIe traces and cables. The PCIe ASPM, or Active State Power Management, is a hardware feature that allows PCIe express links to enter a power state automatically when there's little or no traffic on the link. Basically, the PCIe ASPN support and L01 support is one feature. If you click on the options, you either have disabled, and it's currently disabled, you have the level 1 only, you have the auto, or you have the level 0 support. When you choose level 0, a fast, shallow, low power state, only one directional of the link is affected at a time, and there's a very short latency to reactivate the card. Level 1 is a deeper and more power-saving state for both ends of the PCIe link, but of course with a longer latency to reactivate the card. When in auto mode, the system will decide whether or not it puts it in a power sleep. Out of the box it's disabled, and so your PCIe devices are not put in there. The next feature is Intel VT for Direct I/O, or VTD. This is used for hardware virtualization and allows direct, secure and efficient management of physical I/O devices such as PCIe network cards and GPUs directly to a virtual machine. This can be useful if you want to have a GPU in the system and automatically grant it directly to a VM. The features in here is very basic. You can enable or disable it. I left it enabled even though I'm not using it. Next we have the Intel VMD technology, or Volume Management Device technology, which is a hardware feature to enable management of hot plug of NVMe SSD devices. If we go into detail, we have one property for the first socket, since we only have one CPU, and all three options are disabled. Since I don't really have an NVMe drive in the system, I'll just leave it as is. The PCIe hot plug global option enables or disables hot plug functionality for all PCIe devices, instead of doing it PCIe lane by PCIe lane. And so if we enable it here, regardless of the previous socket 0 configuration lane by lane, hot plug will be labeled for all lanes. And the PCIe ACPI, or Advanced Configuration and Power Interface, is to handle hot pluggable operations like adding, removing and replacing PCIe devices at system level. Again, when this is enabled, this overrides previous individual settings. And finally, the PCIe Express Access Control Services is a security and traffic management feature that provides fine-grained control over how packets are routed between devices on PCIe fabrics, especially in systems with multiple endpoints and peer-to-peer communication. And the features of those access controls are peer-to-peer transaction control, security installation, and blocking or reducing traffic. This is especially important in virtualization servers, where PCIe pass-through is happening to specific and individual VMs, to be sure that one VM only has access to what it needs and no data leakages to other VMs are happening. In my scenario, this won't be used. And then finally, the last block in the socket configuration is the Advanced Power Management configuration. This provides a set of controls for CPU power and efficiency features, designed to optimize performance, reduce power usage, and tailor the system's behavior to specific workloads or energy policies. So it is CPU P state control. This feature allows the processor to dynamically adjust its frequency and voltage in order to optimize the power usage or performance. The speed steps, or P states, are called the performance states. This feature can be enabled or disabled. Each P state is a combination of specific CPU core frequency and voltage. P0 is considered the maximum performance. P1, P2, etc. progressively lowers the frequency and voltage, saving power but also reducing performance. The config TPD stands for the config terminal design power, and you have three options. In normal, the CPU runs at the default. In level 1, the CPU lowers the TPD limit to lower than normal. and reduces the maximum heat out. And level 2 is an even lower TPD limit, but of course restricting the CPU performance. The boot performance mode specifies the CPU performance at system startup, and here you can choose between maximum performance or maximum efficiency or Intel Node Manager. The first two are quite clear. The Intel Node Manager is a configuration that allows to take larger decisions whether or not the CPU can be boosted or not based on some policies that might exist, and which can make a combination of different servers, enterprise or data center wide. If you only have one server at home, it doesn't really matter, and you could choose max performance. However, if you have a rack of 48 and only limited amount of power, you might rather choose for max efficiency. The energy efficient turbo is a CPU feature that dynamically adjusts the processor's turbo frequency based on your current utilization and workload, and optimizes for power savings rather than always targeting the highest possible clock speed. This is enabled by default. If you really need to have your server and your CPU run always at the maximum, then you need to disable this. In line with this, the turbo mode is a form of overclocking, which automatically increases the clock speed above the standard frequency, but only when the system workload, power and thermal conditions permit it. Again, if you want to stay within limits, you can disable the power mode, but you will lose in performance. And then the CPU flex ratio override is a feature that allows you to manually set the CPU core frequency. And when this is disabled, the CPU will use default Intel auto ratios. When this is enabled, you can specify yourself the flex rate at which the CPU can override. If you go too high, you can burn it all down. Of course, this will use again more power. Next, we have the hardware PM state control. This is a feature that determines how much the CPU hardware itself has over entering power saving states, like the P states, idle or throttling. And if you choose to disable, then the power management states are disabled, and so that the OS system is fully in control of what is happening. When we choose the native mode, the hardware uses the P states based on the OS guidance. However, the hardware stays in control. When we choose the out of band mode, then the hardware autonomously chooses the P states and completely ignores what the OS wants. And the latest mode is the same as a normal native mode, but for legacy support, if we need to run older software which don't support the latest version. Next, we have the possibility of overclocking. The Extreme Edition of overclocking specifies the advanced overclocking capabilities available on the Intel CPU processors. These processors are out of the box designed with overclocking in mind and features to unlock multipliers while still staying stable. Next, we have the overclocking lock. When that is enabled, it will still stay within authorized guidelines, and that's mainly important for warranty. If you're more like an enthusiast and you really want to push everything to the limit, you have to disable this. And then next, all of the turbo ratio lines allows you to fine grain and overclock how you want and push your CPU to the limit. Next, we have a CPU C-state control. This is a feature that manages the processor's idle sleep states, known as C-states, which again are designed to save power when the CPU is not doing much. The CPU C6 report is a power saving state which is transmitted to the operating system, allowing the OS to transition the processor in a deep C6 low power state. It can be enabled, disabled, or in auto mode. When disabling, your CPU will never really go into low power state. The enhanced halt state, also known as a CI1, is a CPU power saving mode that allows the processor to enter even a more deeper idle state, and thereby reducing both the clock speed and the CPU core voltage while the CPU is idle. This one can only be enabled or disabled. Related to the CI1, we have the possibility to have a C2 state or a C3 state. A C2 state is stop grant or stop clock, and here the CPU core's main internal and external clocks are stopped. The C3 state is even lower, which is completely sleep. And here the CPU doesn't even respond to external bus activity anymore until it wakes up. Next, we have the package C state control. This is a feature to determine the deepest low power and idle state of the entire CPU package. Not just individual cores, but the whole of a system. And here we have a number of options. By default, we have auto. So when it's in no limit or in auto mode, the system can enter to the deepest available sleeping state. If it's only in C0 or C1 state, it never enters a complete deep sleep or idle state. And this is the fastest wake up. When it's in C2 state, you have a swallow package idle and some power down. And it's still fast to wake up again, but it's slower than C0, C1. However, you gain more in power saving. Next we have a C6, both non-retention or retention. Non-retention is a high power saving and C6 retention is the highest. When C6 retention is active, the context still remains in the SRAM. When C6 non-retention is active, the context is not retained in chip. And the last one, in advanced power management, is a socket RAPL config and its specific Intel features for servers and workstations that lets administrators configure power limits for the entire CPU socket using the RAPL technology. And RAPL stands for Running Average Power Limits. The fast RAPL N-Strike PL2 duty cycle allows the system to go in turbo mode and override default usage, and when we're in 10%, the processor is allowed to consume power for only 10% of the management windows. When we're in 25%, we're allowed to run it in 25% of the management window, which means you can stay longer in turbo mode. The package RAPL limit, MSR lock, and CSR lock are a security and control mechanism used to lock down the processor's power limit settings, ensuring that they cannot be changed while the system is running, except during the full system reset. MSR stands for Model Specific Register Lock, and the purpose is to prevent accidental or malicious modification of power limits after the boot. When it's disabled, that lock is not in place. CSR lock stands for Control and Status Register Lock, and this extends the same concept, but to memory-mapped registers, outside of the model-specific register locations. When it's disabled, this lock is not in place. PL1 stands for Power Limit 1, and this is the long-term, sustained power limit set for a processor, which usually corresponds to the advertised thermal design power. And here we have a number of parameters. We have the limit, we have the power limit, and we have the time window. And PL1 is the long term, while PL2 is a short term. So PL2 mostly refers to turbo usage. Next, we have a server management. These are BMC settings. First, we have a number of statuses. The self-tests are okay. I have a device ID, revision, version number. I have an IPMI version. Then we have an FRB2 timer, stands for Fault Resilient Booting Level 2. It's a feature that uses a watchdog in the baseboard management controller, or BMC, to ensure that the system successfully completes the BIOS post. If the system hangs for whatever reason and succeeds the specified timeout, which is currently at 12 minutes, timer policy will decide what to do. In this scenario, it's configured to reset. Instead of reset, I could choose to do nothing. I could choose a power down or a power recycle. I can, of course, lower the number of boot minutes, or if I don't need it, I can disable it. The OS watchdog timer is in line with the FRB2 timer, but then to validate that the OS is still working on your system. And if in whatever scenario the watchdog timer detects that your OS has crashed or is not responding anymore, then again, we can do the same thing. We can specify timeout 5, 10, 20 minutes, and we can specify again to reset, to power down, or to recycle. Of course, if for whatever reason the OS is still running, it'll just crash the system. Then next, the BMC logo is a nice little quote-unquote logo that is shown in the boot process. Next, we have system event log, and if you go in there, it's the same event log we've already seen in the IPMI. We can choose to enable the SCL component. Of course, we can enable or disable the logging of the system event log component. And finally, when logging, we can use EFI status codes, or just the error code, or just the progress code, or not at all. And the final line is the BMC network configuration, which is, in essence, the IPMI network card configuration, if it's dedicated. And here again, we can choose. Now it's in unspecified. We can specify a static IP. We can use a DHCP, or we can use a dynamic non-DHCP address. I won't change it, it's working. I have the possibility to configure a second port, should I want to use a second port as a shared Ethernet connector. And then also, I can configure IPv6, should I need it. Again, unspecified, static, or dynamic. And this is about the only things you can configure about the IPMI. There's not really a way to reset or to clear out if you don't have any access to the IPMI interface, which is kind of a bummer. The next configuration block allows you to set or change your administrator password and a user password. The administrator password is mainly used if you want to change configuration. But if you put a user password, then every time you boot, you'll have to enter that password. The security frozen mode is a security configuration that protects against unauthorized changes of storage devices after system boot. By default, it's disabled. When it's enabled, the system sends a freeze command to storage devices like hard disks and SSDs during the boot process. This prevents any subsequent changes, override, disabling or removing to drive security features, such as ATA commands, secure erase, until the next full system reboot. This mechanism prevents malware or unauthorized users from disabling or reconfiguring disk security settings, a risk especially in situations where a system might be left unattended but powered on. And then finally, we have a secure boot option. Secure boot is a security feature in modern servers and PCs implemented in the system firmware, the UEFI, that ensures only trusted digitally signed software components like bootloaders, operating system kernels, and drivers can be executed during the boot process. So first we have the digital signature verification. However, when this feature is enabled, some Linux distros won't work since they're not digitally certified. Both versions of TrueNAS don't work with secure boot. Proxmox and ESXi, however, do support secure boot. Next we have the secure boot options, which are either standard or custom. Once we're in custom mode, restoring the factory keys implies that you clean up all the keys you might have added and revert to the initially installed keys. When doing a reset to setup mode, the following things happen. It clears the secure boot keys, it disables the secure boot, it enters in setup mode, but it does not erase data or OS. In essence, you might use this if you clean up your system and you want to reinstall a new OS, which is secure boot supported. And finally, we have a key management. And even though we have a number of PKI keys supplied out of the box, if we really want to, we can add new keys. Here again we have the same option, restore the factory keys. We have again the same option, reset to setup mode. We can export secure boot variables, which might be present on a USB drive or another hard disk. The enroll EFI image allows us to still, with a secure boot setting, install an image which is not secured and or signed. And by using the enroll EFI, we could select that image and still allow secure boot to continue. And finally, we could remove the UEFI certification authority from the database, or we could restore the database back to default. And then here we have the number of certificates which are known. We currently have 1 certificate. We have a key exchange. We have 3 signed authorities. We have forbidden signatures from keys which might be stolen, etc. And so by using key management, we might add new keys should the old ones expire. And then finally, we have the boot options. The setup prompt timeout defines the number of seconds the system will wait or the time you have to press either F2 or del to enter the setup menu. The default is 1 and that might sometimes be too short. The boot numlock state is on, which means that by default your numlock will be working and the quiet boot is disabled. If you enable the quiet boot, then the BIOS will hide all normal post messages and diagnostics showing up on screen. And the only thing you'll see is a logo. Next we have the wait for escape in case of error. If this is enabled and an error happens, the system will wait until somebody types escape. Since this is a server, that might not necessarily be the right thing to do. Next we have the endless boot and the endless boot retry times. So even though we're talking about endless, the endless is limited at about 100. So this happens in case that your boot sequence for whatever reason can't complete and will reboot again. And so this will be keeping rebooting until it fails or succeeds. And after about 100 times, it'll finally stop. In the boot mode, we can choose whether or not we want to boot in legacy or in UEFI boot. Some OSs still don't support UEFI, and you might have to switch back to legacy. And next we have the boot order, where we can specify the devices which need to be booted first. So the boot order currently first tries the network boot. If that fails, it tries a hard disk on which it found Windows. If that fails, it tries a USB stick. If that fails, it tries a CD or DVD, or we could just disable, and that every time the same. So let's say that the first boot, I want to go for USB, and then my second boot, I just want to disable it, and I only want to boot by USB. And so in this scenario, it'll boot from the USB it's found, and it won't try anything else. When I remove the USB, it won't boot at all anymore. Next we have the add new boot option. And in here we can add manually a number of options. Say for instance you have a hard disk which has been partitioned in multiple partitions, and the first partition contains Windows and the second partition contains Linux and the third partition contains something else. And for whatever reason you want to use the second or the third partition which wasn't detected out of the box. Then by using the boot options and the path for boot option, you might specifically choose how the system still needs to boot from the third, the second or the first partition. And in those delete boot options, again, can select one of the options what initially existed. The UEFI hard disk drive, BBS priorities or BIOS boot specification is a configuration screen that lets you set the boot priorities for already detected UEFI capable hard drives. So if we go into detail, currently we have one boot option, and if I select there, the only thing that it found was a Windows boot manager of one of the physical hard drives. Should we have more, we can choose the first, the second, etc. Or we can still choose to disable it. And in line with the first option, the UEFI USB drive BBS priorities is exactly the same thing, but then for USB drives, should we have a system with more than one USB drive, which are both bootable. And then finally, after having changed all those settings, you can choose Save Changes and Exit, or if you change something you don't want to change, you just can choose Discard Changes and Settings and start over. You can choose Save Changes and Reset. The difference between Save Changes and Exit and Save Changes and Reset is that the Reset does a hard reboot, while the Save Changes and Exit just continues the boot process, and some of those changes might not necessarily be applied until next reboot. You can also have Discard Changes and Reset, which is also in line with Discard Changes and Exit, which will force a hard reboot. And then you can also just do a Save Changes without exiting this menu, or Discard Changes and come again. Next we have the Restore Defaults, and that will just restore all factory defaults initially set into the BIOS. And the other two options is to save user defaults and restore user defaults. Instead of restoring to the system defaults, you might first save something as your default settings and tweak around, and after a reboot, restore your user setting. And the last block shows the boot order currently active in this system. I've also attached a physical screen to the TYAN server to show you the full BIOS boot process. On the Dell 13th Gen iDRAC, when connecting remotely, you can see the whole process. Unfortunately, on this TYAN, when connecting through IPMI, this first part is not shown in the remote console. And the remote console stays black until you arrive at the end of the post process and it shows you Dell or F2 or F11 or F12, which is kind of a bummer, because if you really have issues, it might show up in the IPMI, but you can't really see it on your screen without going to see it locally. During the previous walkthrough of platform configuration and SATA and SATA controllers, I enabled the RAID configuration in order to try to set those drives as RAID. Unfortunately, according to the docs, by pressing Ctrl-I, I should enter in the RAID menu. Unfortunately, I tried out every option. When I boot, I never see the Ctrl-I. When I try it, or a number of other configurations, for this server, I can't really seem to get into the RAID menu. So is it really there? I don't know. For my current situation, I don't really need it. But that might be a bummer. So this concludes the in-depth review of the TYAN BIOS settings. I've also done a review on the TYAN IPMI remote management capabilities in another video. If you guys enjoy this content, give it a thumbs up, subscribe to this channel and hit the bell sign. Or leave a comment down below.